Hi everyone and welcome back. So today we're going to start talking about nonlinear systems, which is the last major topic we're covering this semester. So we've been dealing with linear systems up to now, so we're going to go back to nonlinear systems and see what we can do here. So a system of differential equations generally has this form, right? It is several equations for these dependent variables y sub 1, y sub 2 through y sub n, and then we have y1 prime equals f1 of, t and y1, y2 all the way through yn. So this is a first order nonlinear system potentially. The thing that's different here, thing that's new, is that we're going to be allowing these functions f1, f2 through fn to potentially be nonlinear in all of the variables. Before we said, for linear systems, we said that it has to be linear in y1, y2, and so on through yn. So that's the different thing. We have initial conditions over here for each of these different variables, all at the same time point, t0. Right, so as I said, the functions are potentially nonlinear in all variables, and we can then reformulate this by writing the functions in as vector-valued functions. So then we have y prime equals f of t comma y, and then y of t0 is equal to y0. Right, so it's much simpler and more compact to write it in this form. Okay, great. Now we've seen this kind of thing before. So for example, if f of t comma y is equal to a of t times y, so matrix a of t times y plus g of t, then we've got ourselves a non-homogeneous linear system, which is the kind of thing that we solve with undetermined coefficients or variation of parameters or something like that. But we're going to be talking now about something more general, where this is just one particular kind of equation that is a subclass. All right, so where do we go from here? Well, another extra definition here is sometimes there's no explicit dependence of the differential equation on t, so it doesn't appear explicitly. Of course, all of the state variables, or the dependent variables, y1, y2, and so on, do depend on t, but if it doesn't actually appear on its own, then we can rewrite the function f of t comma y as just a function of the y values, and then we call the system homogeneous. Of course, that's a word that we've used many times before. And so the system would then be written as y prime equals f of y, and y of t0 equals y0. So this is the case that we're almost exclusively going to be concerned with in this chapter. Great. So now what can we do with this? The first question we always have to ask is, when can we be sure that unique solutions exist for a system like this? Because those functions can be pretty wild. We haven't put a lot of restrictions on them. Just saying that they don't have to be linear means they could be potentially anything. And that's a little bit scary. So to answer this question of existence, we need to look at, as it turns out, at all of the partial derivatives of the functions f1, f2, and so on. So we have the functions f1, f2, all the way through fn, and then for each of them we take the partial derivative first with respect to y1, with respect to y2, with respect to y3, and all the way up to yn. We do that down the line for each of these. So that gives us n different functions, n different derivatives. You might be noticing a bit of a square structure here. We will be revisiting this as a matrix called the Jacobian matrix later on. But for now, we're just looking at the different partials that we have here. And then what we need to find is, for each of these functions, we need some kind of common domain where things make sense. So can we find an interval for t, an interval for y1, an interval for y2, an interval for yn, where these partial derivatives all exist and, as it turns out, are continuous? If we can do that, then we can put together an existence theorem in the form of theorem 6.1. All right, so you might want to pause this now to write this down. I know it's a long slide, but I'm going to move on to the theorem. So what does 6.1 say? It says, okay, well, let's consider this initial value problem. Y prime equals f of t comma y with y of t0 equals y0, where the initial point t0, y0 lies in the region R defined in the previous slide. So that's where we have these intervals, right, the rectangular region R. Okay, so t0, y0 is in there. Now, suppose also that f of t, comma y, and all of the partial derivatives that we saw in the previous slide, suppose those are all continuous in this region R that we found. Then we can say that the initial value problem has a unique solution, y of t, that exists on some t interval, CD, containing the initial time. So we get unique solutions existing for some time interval. But, and this is important to note, as in the previous cases when we're dealing with a single nonlinear equation, the theorem doesn't tell us how long this time interval can be. It only tells us that there is an interval. It could be quite small. And that's, again, because of the nonlinearity. You can make all kinds of crazy things happen with nonlinear functions. So this is our basic existence theorem. Let's take it out for a bit of a spin. Let's apply Theorem 6.1 to the following system. This is a system that describes the dynamics of two competing species whose populations are given by P1 and P2. So just a little note of what's going on here. Here we have the rate of change of population 1 is some big thing here times P1. So that means it's proportional to its current population size. And then this remaining part here is the per capita growth rate. And if we look at the parts of that, so the per capita growth rate of species P1 is R1 times 1 minus alpha 1 P1 minus beta 1 P2. Okay, so what does this mean? Well, this is the per capita growth rate. It's some constant, so constant times 1, but that constant growth rate is reduced by the population itself. So this represents a kind of intra-species competition. So having more of your own species around makes it harder to find space to reproduce, find resources to survive. And then the other one is the presence of the other population makes it hard to reproduce. So this is inter-species competition. All right. So that's what's going on in this model. Basically, we have two species that are interfering with each other's ability to reproduce. So it's a model of competing species. Usually two species, not necessarily competing with each other, but maybe competing over some common resource. All right, so that's all kind of beside the point for Theorem 6.1. What we want to check is, do solutions for this set of differential equations exist for some given initial condition? And what we need to look at is all of the partial derivatives of the right-hand sides of this equation, right? Because this right-hand side here, this is F1 of P1 and P2. This one is F2 of P1 and P2. So we need to look at our partials. So what will we have? We need the partial derivative of F1 with respect to P1. This is a little bit, you've got to do some product rule and things like that. We get R1 times 1 minus alpha 1. Well, let's do it the other order. Sorry. So we're just going to we have a constant R1 times something. So we're going to do the product rule to be R1 times minus alpha 1 times P1 plus R1 times 1 minus alpha 1 P1 minus beta 1 P2, and that's it. And we can simplify that to R1 times 1 minus 2 alpha 1 P1 minus beta 1 P2. And that's a nice continuous function, right? It's continuous everywhere. It's a polynomial in P1 and P2. So that's a pretty good sign. Similarly, we can take the partial of F2 with respect to P2. And that one's a little bit simpler. We get minus R1 beta 1 P1. Okay, we now need to find partials of F2. Partial of F2 with respect to P1 is equal to R2, so minus R2 beta 2 P2, because the only term with the P1 in it will be R2 times beta 2 P1 times P2. And the partial of F2 with respect to P2, by a similar calculation to what we had before, will be R2 times 1 minus beta 2p1 minus 2 alpha 2p2. So we have four functions here that all need to be continuous, along with the original functions f1 and f2 have to be continuous at a given point in order to have the existence of a unique solution at some time interval around that. And thankfully, these functions are continuous everywhere. So we don't have any problems. Theorem 6.1 will apply at any initial condition you could dream up for this set of equations. You'll be guaranteed a unique solution, at least on some time interval after that. All right, let's try another one. So this is an example that we're going to revisit from time to time. The simple pendulum, no friction, no drag, although the diagram has a little bit of drag indicated on it. So basically the idea is we have a pivot point up here and then a string of some sort hanging down. The length of the string is L, and a mass at the end of it. So we're assuming a lot of simplifying things with this, but this pendulum is now swinging, right? It swings back and forth, and we have a force of gravity pulling down on it, and we have its momentum in whatever direction it's going, and we have to figure out the angular velocity in order to get a differential equation for this variable theta, because that's going to change with time, right? The mass doesn't change, but that one does. So with a little bit of help with physics and geometry and things like that, we figure out this force in the direction that we need it, which ends up being mg sine theta, and we get this differential equation for the angle of the pendulum, which is, if you know the angle of it, then you're going to know what its position is. So our challenge here is first to convert this into a system, a first-order system of nonlinear equations instead of a single second-order equation, and then apply Theorem 6.1 to see if we get unique solutions. So we're going to do that over here on the next slide. So here it is again. That's the same equation. Let's go to work. So the trick that we do in order to make this work is we are going to start by saying, okay, I'm going to define a variable y1. It's going to be equal to theta, the thing that I'm interested in doing. And then y2 is going to be equal to y1 prime. Right? And that's going to help us. We're going to be able to write everything, all the information about this system just in terms of y1 and y2. So differential equations, y1 prime, well, that's equal to y2 by definition, right? That's right here. We just wrote it in the opposite order. And then what about y2 prime? Whoops. What about y2 prime? Well, that is equal to y1 prime prime. So that's theta double prime. And from our equation up here, theta double prime should be equal to negative g over L sine theta. So now we have a system of differential equations. We have y1 prime equals y2, and y2 prime equals minus g over L sine of y1, right? That's the last step I forgot to put in there. Theta, of course, is equal to y1. So now we have an autonomous system of differential equations, two first-order nonlinear equations, right? Nonlinear because that sign is in there, right? Sine of y1 is nonlinear. So if we want to apply the theorem, we need to apply it to these two functions. This is f1, this is f2. So the partial of f1 with respect to y1, the partial of f2 with respect to y1, the partial of f1 with respect to y2, and the partial of f2 with respect to y2. We need to calculate all of these. So give this a try yourself, and then come back and see that you got in agreement with me. All right, so what do we have? Well, for the first equation, it has no y1s in it, so that partial is 0. The partial with respect to y2 is 1. The partial of f2 with respect to y1 will be minus g over L cosine of y1, and the partial of f2 with respect to y2 will be 0. Again, we have four functions to consider here, 5 and 6 if you consider f1 and f2. All of them are continuous on the entire real line. So again, any initial value condition, any initial value problem that we could put together with this, right? Giving it an initial position, theta, and an initial velocity, theta prime, which would be our y1 and y2. Any of those would result in